Let me introduce myself. So I am Thanh Võ. I am a PhD student at Western University under the supervision of Professor Boris Monokovic. And today I would like to talk about the derivative-based Newton methods, the composite optimization. Okay, so the talk is based on the joint book with Phạm Duy Khánh, Professor Boris Monokovic, and my friend Michael. Okay, so before I move on to the main part of my talk, I would like to report something about the classical Newton method. So this classical Newton method was recalled in the previous talk by Nat, and I will not talk this anymore. But the disadvantages of the classical Newton methods is that it will not have the global convergence, right? So the technique to overcome this disadvantage is use the license to attain the global convergence. But when we use the license strategy by using the Newton direction, the disadvantage here is we need the positive definition of the Hessian metric, right? But in some cases, the positive definition of the Hessian metric will not be satisfied. So we will not get the extended direction in this case. So in the case the Hessian metric is merely positive semi-definite, the Newton direction will be not assist. So to overcome this difficulty, so the simple technique is using another direction, not the Newton direction. The technique here is use the Levenberg model technique. That's we replace the Newton direction here by this solving the satisfy this equation. Okay, we will find the k satisfy this linear equation, and the resulting algorithm using this direction is called Levenberg method. Okay, there are lots of papers investigating this method. So they use a lot. I show you here 3 papers about the Levenberg algorithm, and they show that the rate of convergence here is very efficient, and but the method here is a C2 case. But our purpose here is develop this method for the non-smooth case. Okay, so the question here is how to develop the generalized Levenberg model based on the generalized differentiation. Here we choose the limiting coderivative. Why we choose this tool of variation analysis to establish the Levenberg model method? There are 3 reasons for this extension. The first one is the limiting coderivative has a comprehensive calculus rule, and the second one here is limiting coderivative have complete characterization of metric regularity, which play the crucial role in variational analysis optimization. And we know this characterization is Monokovic criteria, and this is very useful for characterize the metric regularity. And the third reason here is limiting coderivative will have the implicit calculations in a number of important structures. And that's the reason we choose the limiting coderivatives to establish our algorithm. Okay, and in this talk we will design and justifications of local convergence Levenberg model algorithm based on the second order subdifferential or the coderivative of subgradient mapping for C11 optimization problem. And after that, we will develop and establish the Levenberg model for non-smooth class of optimization. We choose the convex composite optimization problem in this case, And finally, we will give you the numerical results of our algorithm and compare with the one of the highly efficient method to solve lots of problem. It's called the semi-smooth Newton augmented Lagrange method. Okay, that's the purpose of our talk, my talk today. And here I will recall some notion in the tool of variational analysis, but was also recalled in the previous talk of that. And now I just give you quickly about that. And these notions are presented in the book of Mordkovich and Rockefeller. And you can find the book here. And we have the normal cone for the derivative and subdifferential. And the main tools of our algorithm here is use the second order subdifferential. That means we use the co-derivatives of subgradient mapping to establish our algorithm. Okay, so the first one here is the co-derivative based Levenberg-Markov in C11 optimization. Okay, so the difference between our algorithm and classical Levenberg-Markov here is in the step 2, right? We just relate decay by solving the linear equation by solving this inclusion. And we just relate the Hessian matrix by the second order subdifferential in this case, because in C11 optimization we don't have the Hessian matrix, okay? And all the steps here is similar, is the same as the classical Levenberg-Markov algorithm. And okay, so now we will talk about the convergent behavior of this algorithm. Okay, so the first result here is if we have the second order subdifferential is positive semi-definite in the level set here, then we have two statements. Okay, and the first one here is the algorithm. And our algorithm will stop after finally many iterations, or it will produce a sequence that make the sequence of values is decreasing. That is the first statement. And the second one is if x bar is the limiting point of the sequence, so x bar will be a reciprocal point of the cost function. So that's the two statements the result about the convergent behavior of our algorithm. But the thing here is, what is about the convergence? What is about the convergence of the algorithm when this algorithm converge? And the further question is, when we have the convergence, what is about the rate of convergence of this algorithm? Okay, that is two questions we talk next. Okay, and we will need to have more conditions about that. And before I move on to the answer the question I mentioned, I have to recall some concept in variational analysis. The first one is the metric regularity. Okay, the metric regularity is defined in the slide here, and these properties can be characterized by Mordkovich co-derivative or limiting co-derivative, and it's called the Mordkovich criteria. And we can use the co-derivative here to characterize the metric regularities of the set value mapping. And this criteria can be found in the paper of Mordkovich here. I cite here. And the second one here is the field stable local minimizer that was presented by Bollington and Rockefeller in 1998. And here is some paper about that. The first one is the seminar paper about the field stable local minimizers by Bollington and Rockefeller in 1998. And after that, Rusavicki and Lewis established the relationship between the field stable local minimizer and the strong metric regularity of subdifferential in the paper in the 2020. And in 2015, Morovic and Meyer established the second order characterization of this stable localizer and application to nonlinear programming here. And there are lots of papers about using second order differential to characterize this stable localizer, not only for unconstrained optimization but also for constrained optimization. Okay. And another notion that's very crucial here is semi-smooth start. This notion was presented in 2019, but was published in 2021 in the paper entitled "On a Semi-Smooth Star: Newton Method for Solving Generalized Equations" by Jeffrey Auchata. And the class of set value mapping is satisfied. This property is very large, and it's easy to satisfy in a lot of Rousseau situation. And this is the intention of semi-smooth mapping. You know that about the semi-smooth mapping is just defined for the locally single value mapping. But the semi-smooth star here is not just defined for the single value mapping. It's defined for the set value mapping and not just for the locally single value. And here is a very strong, very crucial notions. Okay. Okay. So now we are ready to attend the level of competence and the rate of competence of our algorithm. The first one is if we have more condition that means we have the magic regularity of the radius around the limiting point, and we will get the first statement here is the H bar here is the Q-stable local minimizer, not just the local minimizer. We have this one, and the sequence of value and the sequence of radius mapping will converge, and at least Q linearly and R linear respectively. And the convergent rates of these sequences are Q superlinear if we have the radius mapping is semi-smooth star and one of these conditions hold. Okay, so these results are very crucial because it's elaborate to connect the C11 smooth to not smooth result. Okay. So now we move on to the non-smooth optimization problem that we choose the convex composite optimization to investigate. Why we choose this optimization problem to investigate? Because it covers a lot of structure in optimization, like the constraint optimization problem, lasso problem, convex clustering problem, and so on. And not only that, it's also be a sub-problem of many algorithms like augmented Lagrange, proximal point algorithm, so on. And here we have to recall some notions about modal envelope and proximal mapping. That were presented in the book of Rockefeller and West, Variational Analysis in 1998. And here we have another notion. Here is forward backward envelopes. The forward backward envelope is the extensions of modal envelope. That is the extent for not only the one function, is the extent for the that function have a sum of two convex functions. Here we have the function phi is the f plus g, where f is a function smooth and g is not smooth, and the forward backward envelope defined as follows. And as you can see, when f is equal to 0, the forward backward envelope will be reduced to the modal envelope. Okay, that notion was firstly introduced by Marginov and Bamboras in 2013 in the paper Rosmo-Newton method for convex composite optimization. The motivation of this notion here is they want to give another notion to solve the composite optimization instead of using the Rosmo-Newton method to solve this problem. Because in some cases, Rosmo-Newton method cannot be used because of the complication of subproblem. So they use the forward backward envelope to solve the convex composite optimization. And very recently, the group of Pachinov established the forward-backward algorithm, forward-backward envelope to solve the non-smooth optimization problem, not only for convex optimization, but also for non-convex optimization. And here, we present some the differentiability of forward-backward envelope. Here, if we have the function f is C2 smooth and convex function, and G is convex function, then the Ross radial mapping here is single value elliptic continuous. And the second statement here is the forward-backward envelope here is C1 smooth, and the gradient of forward-backward envelope can be computed by this formula. Okay, and you can see that if we have this one, by this property we can pass the non-smooth problem to unconstrained non-smooth one. Here, instead of solving the minimize of function phi is equal to f plus g, we can solve the problem 11. Okay, and as you can see that the function phi gamma is not generally C11 smooth, so we will focus on the case that the forward-backward envelope is C11. That means the function f here is quadratic function. And as you can see in the equation 10, if the function f is quadratic function, then the radial mapping will be logarithmic. And after that, we will consider this case to investigate our algorithm. So we have to give some result about the forward-backward envelope between the ratio between the forward-backward envelope and the initial function. The first one here is we will calculating the general line SR of forward-backward envelope. As you can see, the second order subdifferential of forward-backward envelope can be computed by through the second order subdifferential of G, and the G here is more easier than compute the second order differential of forward-backward envelope, right? And the second one here, we will establish the metric regularity and tensile stability between the forward-backward envelope and the initial function. Here we have this result. Instead of we check the metric regularity of forward-backward envelope, we can check the metric regularity of the initial function and the core function here. And instead of we find the local minimum stable local minimizer of forward-backward envelope, we can find the stable local minimizer of the function phi. Okay, that's the second result about the metric regularity and stability of forward-backward envelope. And here is the relationship between the semi-smooth star and the rational differentiability of forward-backward envelope. Here we have this result. Instead of checking the semi-smooth star of the forward-backward envelope, we can check the semi-smooth starness of the subdifferential G. So it's easier than we check it directly the semi-smooth star of the forward-backward envelope. And here we have our algorithm for the Levenberg-Marquardt for solving non-smooth composite optimization problem. Okay, so that's the algorithm here. And we have the convergence behavior of our algorithm. We assume that the metric here is positive semi-definite, just positive semi-definite. And after that, we have some statement about that. The first one here is that our algorithm will stop after finally many iterations, or it will produce a sequence that makes the value of function decreasing. And the second one here is if we have the subgradient mapping phi is metric regularity around the point x bar 0 with some modulus, then we will have the stability of the x bar, and the convergence of the x bar will be attended, and x export irreducible local minimizer. And here, the rate of convergence here is Q super linear if we have the subgradient mapping is semi-smooth star. And in some algorithm, they will not give the assumption subgradient mapping is semi-smooth star, but they will give the semi-smooth of the Rossimo mapping. And in some cases, the Rossimo mapping will be harder to calculate than the subgradient mapping. So the subgradient mapping here is easy to calculate in compare with the calculate Rossimo mapping. And then we can check the semi-smooth star of the subgradient mapping easier than we check the semi-smooth of the Rossimo mapping. And here we will use some numerical experiment to solve lots of problems. And we will compare our algorithm with the highly efficient semi-smooth Newton augmented Lagrange methods, which were introduced by Lee, Sun, and Paul in a paper entitled "A Highly Efficient Semi-Smooth Newton Augmented Lagrange Method for Solving Lots of Problems." And in this paper, they used the hybrid algorithm that combines the augmented Lagrange method with the semi-smooth Newton method to solve lots of problems. And here, we will use the random data to make the numerical experiment. We will divide the numerical experiment into two parts. The first one here is we will set the starting point as all one vector, and we will choose b is equal to 0. In this case, 0 is the solution of our algorithm, and in this case, we will use the stopping criterion is the values norm sk is less than some parameter. Here we choose the parameter is the 10 to the power negative 6. Okay. And in the second part, we will choose the stopping criterion is the KKT residual here. It was suggested by the Fanson, and he said it's useful to use it to measure the approximate solution. And here we will choose two stopping criteria in two testing process here. Okay, so we will talk about the part one of our numerical result. If you can see that we put 5 star, 6 star here. We will start here to indicate that the data here is not A star here. The matrix A here is singular. When we put star here, that means that the matrix here is singular. And as you can see that our algorithm here is very efficient. Efficient in the case the data is non-singular and in the low dimensional space. But in the high dimensional space, we will be not good as the algorithm of diffraction. Okay, so it's similar to the part two of numerical results, and our algorithm will be very efficient in the case the data here is not singular and in the low dimensional space. So in the future, we want to develop and improve our algorithm in the case high dimensional space, and we will combine with some other efficient first order algorithm to solve more class of optimization problem. So that's our investigated in future research. Okay, so that's all things I want to talk today. Thank you for listening.
Any questions? Any questions from remotely as well? Can you ask them? Can you ask them?
Is there any question for me?
All right, well, let's thank our speaker again.